Now we introduce the second lemma in Eisenstein's proof of quadratic reciprocity law. This lemma gives a trigonometric formula, writing sine of mx, where m is a positive odd integer, into products. It states that sine of mx divided by sine of x is equal to -4 raised to the power n minus 1 divided by 2 times the product for j from 1 to n minus 1 divided by 2 of factors sine of x squared minus sine of 2 pi j divided by m squared. So now let's prove this. We're going to break this proof into a couple of steps. In the first step, let us first show the left-hand side is a polynomial in sine of x squared of degree n minus 1 divided by 2. To prove this claim, we're going to first write sine of mx into a sum. I'll first write what this is, and then I will explain. In this formula, we write sine of mx into the sum from r equal to 0 to r less than or equal to n minus 1 divided by 2. And summands are these telescoping terms. And this sum looks like a binomial sum. To verify this, we use complex numbers. We consider e to the power I.Mx, which can also be written as e to the ax raised to the power m. And now using the Euler's identity, the left-hand side is cosine mx plus I sine mx. And the right-hand side is cosine of x plus I sine of x raised to the power m. And this formula can be derived from here by comparing the coefficients before the imaginary unit I on the both sides. The left-hand side is easy. We just have sine of mx. The right-hand side is slightly more complicated. We have to look at the binomial expansion for this. And we only have to focus on those terms that are imaginary, namely when k is an odd number. If you write k equal to 2r plus 1, then a generic term on the right-hand side that is imaginary will look like m choose 2r plus 1 times cosine of x raised to the power m minus 2r minus 1 times sine of x raised to the power 2r plus 1, and this is I raised to the power 2r plus 1. But I raised to the power 2r is -1 to the power r. So we can rewrite this as -1 to the power r times I. And this is precisely this. Summing this up from r equal to 0 all the way to 2r plus 1 less than or equal to m, this identity is verified. And now let's see how this identity implies that sine of mx divided by sine of x is a polynomial of degree n minus 1 divided by 2 in sine of x squared. To that end, we're going to divide both sides by sine of x. From here, we see that this part is already a polynomial of sine of x squared. This part can also be transformed into a polynomial of sine x squared by using identity that the cosine x squared plus sine x squared is equal to 1. So now let's rewrite this. Now for each summand, we can easily see that it is a polynomial in sine x squared of degree n minus 1 divided by 2. But our goal is to show that the whole sum is also a polynomial of degree n minus 1 divided by 2 in sine x squared. So to this end, we have to also compute the leading coefficient for this polynomial in sine x squared. We have to show that leading coefficient is non-zero. So now we look at the right-hand side of this identity. The coefficient of sine of x to the power n minus 1 divided by 2 is the following. It is the sum from r equal to 0 to n minus 1 divided by 2. And we have -1 to the power r, and the binomial coefficient m choose 2r plus 1, and the coefficient here is -1 to the power this. And this part cancels with this. What we get is and now it remains for us to figure out what this guy is. To find out what this thing is, we consider the binomial expansion for 1 plus 1 raised to the power m. And we're going to split the binomial expansion of this into the even terms and odd terms. And we do this again for 1 minus 1 raised to the power m. And we subtract both sides of this from both sides of this. So this is just 0. And for the right-hand side, we get 2 times the sum for the odd terms. And simplifying this, we get, and the left-hand side can also be written as 4 raised to the power n minus 1 divided by 2. And plugging this guy back to here, we get -4 raised to the power n minus 1 divided by 2. And this is the leading coefficient, the coefficient before this term. And in particular, it is non-zero. And to summarize what we have obtained so far, we have obtained that the sine of mx divided by sine of x is equal to 94 raised to the power n minus 1 divided by 2 times sine of x squared raised to the power n minus 1 divided by 2 plus lower order terms in sine of x squared. So this is indeed a polynomial in sine of x squared of degree n-1 divided by 2 with leading coefficient -4 raised to the power n-1 divided by 2. Now to finish the proof of this lemma, it suffices to show that sine of mx divided by sine of x as a polynomial in sine of x squared of degree n-1 divided by 2 has these numbers for j from 1 to n-1 divided by 2 as its roots. And those numbers are actually distinct. So by the unique factorization theorem for polynomials, we know sine of mx divided by sine of x must take this form. And I'm going to write this as claim 2. This is our last step. Let us first verify that these numbers are indeed distinct. This is because if j and j prime are not equal and between 1 and n-1 divided by 2, then sine of 2 pi j divided by m squared equal to sine of 2 pi j prime divided by m squared implies, noting that j and j prime are both between 1 and n-1 divided by 2. So the angles in the parentheses will be angles between 0 and pi. So this equality still holds even if we drop this square. And because those angles are between 0 and pi, and j prime are not equal, so the only case for these two to be equal is when their sum is equal to pi. Or equivalently, j plus j prime is equal to m divided by 2. But this is impossible because we have already assumed that m is an odd number. There's a contradiction to the assumption that m is odd. Left hand side is an integer and right hand side is a half integer. So these n-1 divided by 2 many numbers are indeed distinct. So in the second step, we're going to show each of them is a root of this, viewed as polynomial of sine x squared. So how do we verify this? This condition is equivalent to sine of x equal to plus minus sine of 2 pi j divided by m. And this happens if and only if x is equal to plus minus 2 pi j divided by m, or pi plus minus 2 pi j divided by m modulo 2 pi. And this last line always implies that sine of mx is equal to 0. So this polynomial vanishes at sine of x squared equal to this for any j. And this finishes the proof of claim 2. And by the unique factorization theorem for polynomials, we have proved this trigonometric lemma. The leading coefficient is this guy, and degree is n-1 divided by 2, and the roots are these numbers. Now with these two lemmas in hand, we can provide the second proof of the quadratic reciprocity law due to Eisenstein. Let L and P be two distinct primes, different from 2. And we want to show that the Lagrange symbol of P modulo L is equal to -1 raised to the power epsilon L epsilon P times the Lagrange symbol of L modulo P. To use the Gauss lemma, as before, we're going to take S to a set of integers 1 to up to P minus 1 divided by 2. By Gauss lemma, we have L over P is equal to the product of E sub S of L for S ranges over capital S, where this ES of L is defined by the following equation. And recall that this ESL is plus minus 1, and this SL is also in S. And now we're going to apply a function to both sides of this equation. We're going to apply sine of 2 pi divided by P to both sides of this. And what we get from here is the left-hand side becomes sine of 2 pi divided by P Ls, and the right-hand side is sine of ESL 2 pi divided by P SL. And remember, this ESL is plus minus 1. And sine function is an odd function, so we can pull it out. And now let us recall a very important property about SL. Remember, in the proof of Gauss lemma, we have shown that the map sending S to SA is a bijection of S onto itself. And here, the map sending little s to SL is also a bijection. So now we're going to multiply both sides of this equation for little s ranging over S. For the right-hand side, we can break this into two parts. And now, if you look at this thing, because the map sending S to SL is a bijection of S onto itself. So this part can be rewritten as just a product of sine of 2 pi divided by P times S for S ranges over capital S. Now what about the first part? The first part, by the Gauss lemma, is just the Lagrange symbol of L modulo P. And now let's see what we have concluded from here. If we move this product to the left hand side, we see that the rounded symbol of L modulo P is equal to the product for S ranges over capital S So this is what we have concluded from the argument above. Now we are going to apply the second lemma to this identity we just obtained. We're going to replace each factor on the right hand side by this product. And to this end, we take m to be L and x to be 2 pi divided by p times s. And we're going to replace j by another variable t for convenience. So by this lemma, we have and because this capital S is a set of integers from 1 to p minus 1 divided by 2. So we can replace this capital S by something more explicit. So this little s is from 1 to p minus 1 divided by 2. And next, we're going to pull this negative 4 to the power L minus 1 divided by 2 outside. Remember, this is a product with p minus 1 divided by 2 many factors. So when we pull this out, what do we get? We get the extra factor p minus 1 divided by 2 because they are p minus 1 divided by 2 many terms. From here, we see there's a very beautiful symmetry that we can take advantage of. Switching the roles of L and P, we have a dual version for this identity. And from here, we would like to put the term involving P in the first place and the term involving L in the second place. Namely, we want to swap these two. And swapping all of them will create an additional factor, negative 1 to the power this thing times this thing. And now, let me put this to the front and this to the second place. And compare this with this. What do you find? We see that they are precisely equal to each other. The only difference is that the rows of T and S are swapped from here to here. But that doesn't matter because S in here is from 1 to L minus 1 divided by 2, which plays a role of T in here. And T in here plays a role of S in here. Because the range for S and T is also swapped. So this product is same as this product. So they are equal. And therefore, the last line becomes negative 1 to the power L minus 1 divided by 2 times P minus 1 divided by 2 times the rounded symbol of L modulo P. And from here, you can see that we have already proved the quadratic reciprocity law. Because this guy is equal to this. So we have proved that the rounded symbol of P modulo L is equal to negative 1 raised to the power epsilon of L times epsilon of P times the rounded symbol of L modulo P. So this finishes the second proof of quadratic reciprocity law due to Eisenstein.